Thank you very much. So first of all, I wish to thank the organizers for the very pleasure to be here at this conference, listening to so many interesting talks. So today I will tell you about noise sensitivity of random walks on groups, and this is a joint work with Itai Benjamini. And the paper is not yet on the archive. It hopefully will be there very soon. The results I will mention, they are written down, but kind of the overall picture, we still need to write this down. So of course, here there's no need to explain what are random walks on groups, because there are so many experts. But noise sensitivity of random walks on groups is a kind of new topic. So first, noise sensitivity is not at all a new topic in general, right? Since maybe at least maybe Shannon, he had this theory of information, and he was interested, you know, if you noise a message, then can you recover it, and how much redundancy you need on this message to be able to recover it. Noise sensitivity was studied, for instance, also in this question of elections process, like if you have an election process and maybe a few proportion of people, you know, they cannot vote on the day of the election. Does it have a serious impact on the result or not? So this was studied in many ways, for instance, by Gilles Calais and many collaborators. Noise sensitivity is also a very familiar topic in percolation theory. For instance, of course, Itai Benjamini and Oded Schramm and many other people. I must say I don't know a lot about all this history. But what will be new in this talk is that we will study noise sensitivity of random walks on groups, and this so far has not been really considered. So let me explain the general picture. So we start with a group G, and we take a measure mu, so that's a probability measure. I will assume finitely supported. I really don't believe this is important, but okay, it's just you know, to restrict the landscape to explore. So the probability is finitely supported, and the support is generating. Generating in the sense of semigroup. And so what is the random walk? So you take a sample of the random walk. It's a xn. It's a product S1, S2, Sn of random variables Si. They should be IID with the same low mu, right? So how do we think about it? We think of this, I mean, often you can think about it as, say, a path in the K-graph or a walk in the group. So the increments here tell you how to move, and you get a trajectory out of this. And noise sensitivity is about the following question. Now imagine you have some noise. So what is the effect of noise? This modifies your sample. So I have a noised sample, which I will denote by y sub n. So now it's a product R1, R2, Rn, where Ri, well, you have two possibilities. Possibly there was no noise at time I, then Ri is just Si, the very same entry as in Xn. But possibly there is some noise, and you have Si prime, which is an independent sample of low mu, independent and low mu. And of course, you have to decide when you do one or the other. So let's say we fix a parameter rho between 0 and 1. And, well, let me have the good convention that we refresh the increments with proba rho, and then this we keep with the probability 1 minus rho. So to make this precise, we would need to take first epsilon would be random entries between zeros and 1, and then we take it each of them to be Bernoulli of rho 1 minus rho, and then we decide whether we should resample or not according to this one. So,
sorry, from which distribution do you sample the noise intervals?
so this one?
Yeah.
So it's the same law. It's still the law mu, and it's an independent one. So the way to think about it is, okay, you know the law mu, and now I'm telling you, say on the phone, a trajectory, but I can't see where you are. And I'm telling you, okay, you do this move, this move, this move, this move. And sometimes there is noise, you cannot hear the move, so you make a random move instead. And the question is very, very simple. We say,
Isn't
yeah.
it random already? The increment. So what's the difference between its randomness as an increment, as a single increment, and its randomness?
Yes. So if you take it as a single random variable and look at xn alone or at yn alone, of course they have the same law, that's for sure. But now we are going to look at question is somewhat, if you know xn, or what can you say about yn, or if you know yn, what can you say about xn? Yes?
So if you visit that site and you already know value, right? You know, but then you can resum.
Sorry? If? I resample according to time, not according to site, right? It's So okay, the general picture, what we say is, the idea is we say a group G mu is noise sensitive. Let me be vague. If yn rho, this is the sample, so I try to remember the parameter rho, but maybe it's not so essential. Yn rho resembles an independent sample, xn prime. So if knowing xn tells you almost nothing about y, or yeah. Yes. I will make it precise in two different sense, and I mean you can coin out several other ones. But so okay, I need to be more precise. Okay, so let me be precise from the start. So okay, so
That opportunity has already been lost.
thank you. Okay. So okay, denote the law of the couple xn yn rho. I denote it by pi sub n rho. So I take the couple of these, and so we can express it, by the way, in a very explicit manner. Right, so at each time, in fact, if you look at both of them, then you're making a random walk on the product group. And so with probability 1 minus rho, you take the diagonal measure, right? U is just the, you take S1 and R1 to be equal. And with probability rho, then you take mu times mu. And then you take the nth convolution of this. So this is really making a random walk on the product group. And, well, we say, so here is the precise definition, number 1. So let me say it's L1 noise sensitive if, so you take the L1 norm of the difference between the distribution of xn and y and o, and you compare it with the product measure, like to take independent random walks on G times G. And then you take either, well, I use the L1 norm, but of course it's just twice the total variation, so the vocabulary is the same. And then we say it's L1 noise sensitive if this difference tends to 0 as n tends to infinity, and we require this for any rho in 0, 1. Right? So even if you perturb extremely little, like 1%, noise, then we still expect, if the group is L1 noise sensitive, we still expect that the distribution will look almost like the distribution of two independent samples. Okay, so let me give some examples where this occurs. And the first example is maybe may be obvious, or maybe, oh, maybe. Okay, I wondered from the start of this conference how I would manage with this blackboard, and still haven't found out how. But okay, examples of L1 noise sensitive. So here is a degree 0 example is finite groups. So of course, finite groups, what happens is that if you take this measure, or just mu times mu, then eventually this will get equidistributed on G times G. So it's true that they will converge to the same. But somewhat is really not interesting example, because the real question about finite groups will be, does this happen before or after mixing time, right? So it's really, I mean, it's an example, but for a bad reason. And the question is, are there other examples? So we'll see. We'll get to the answer of this later on. And let me first explain non-examples, right? So the first non-example is, okay, you start finite groups, then you take a little bit more. So the first infinite groups that you would think of is Z, right? So what happens with Z? So what happens is that, well, the distribution of xn is going to be given by a Gaussian, and then the width of this Gaussian is like root n, comparable to root n, right? And if you noise with the parameter rho, then, okay, you can push your noise all the way to the, as it's a commutative group, then it's really like you have the same thing for 1 minus rho times n time, and rho percent of the time you have different things. So it happens that if you know xn, then the distribution of yn, it will also be a Gaussian, but very, very, very much concentrated. Now the width is like square root of rho times n. So it's very clear that this group is not L1 noise sensitive, right? Even the smaller you take rho, then the limit of this will tend to 2, right? As rho tends to 0. And already this gives an interesting constraint. So here is a corollary. So if a group is L1 noise sensitive, then it must have no morphism to R, besides the trivial one, of course. So okay, I wrote Z, but of course you can put R in the same for the same argument. So it must have. And the reason is fairly obvious, right? The proof is just that L1 noise sensitive, obviously this is defined by L1 convergence, so this passes to quotients. So that's an obstruction. Okay, so we tried with small groups. Let's try with the bigger groups. Like, okay, in the opposite spectrum, second non-example, maybe I can put it here. Oh no, this part of the board we should not use, right? So second is the free group. So what happens in the free group? So okay, let's first, before telling what happens in the free group, let's make an observation, is that if you have L1 noise sensitivity, you have this convergence to 1. So it implies in particular the following convergence, that if I take this distribution, so this mu times 2 star n minus 1 minus mu times 2 star n, and I take the L1 norm, this tends to 0. So what is this? This is just what happens if I know I sample 2 random walks. So I sample 2 random walks in the group, and here I sample 2 random walks that have the same starting point. I'm just using the starting point. So it's really, I'm interested in the first increment of this. If they have the same increment in the free group, then already they should. So if we have L1 noise sensitivity, then this implies that if we start with the same increments, this does not impact this. So we can, get this from here. It's just we take the first factor here. So 1 is like a portion of is rho times mu. So this will simplify, and then we are left with mu diagonal star pi n minus 1 rho minus this, and you use this convergence with n minus 1 instead of n. So you get to this fairly easily. And if you take two random walks starting from, say, here, well, what is the probability that you land in here? So if you start from here, you have 3 chances over 4 to end in here. So if you take 2 independent, that's 9 over 16. But if they start from here, it's like 1 over 4, and then the square is like 1 over 16. So there's a big difference between 9 over 16 and 1 over 16. So this is very different. And in fact, this can be carried out to the general setting. And here is the first maybe theorem. If you have L1 noise sensitivity, then the group G and mu, they have to be Liouville. So at this stage of the conference, there's no need to define Liouville groups, I guess. So let me try to prove this theorem. So let me proceed the other way around. Assume if not Liouville, then there exists. I claim that there exists some set in the Poisson boundary of a non-trivial measure. This will be clear, such that if I compute nu of A square is strictly less than the sum G in G of mu G nu of G inverse A this square. So let me explain about this. This is very easy. This is a well-known fact. There must exist such a set. Why? So if I remove the squares, then I have equality, right? Because this is just saying that so nu is the harmonic measure on the Poisson boundary. So this is just saying that the harmonic measure is stationary. Now, I have this Jensen inequality, so this gives a large inequality here. Now, assume that for any A, we have actual equality, not strict inequality. Then, if we have equality by equality case in Jensen, this means that this nu of A is equal to ni G inverse A for all G in the support and for all A. And out of this, you'd get that nu is actually invariant, so the Poisson boundary would be actually trivial. So we have such a set like this. And well, then how to say? So by stationarity, this thing can be expressed in terms of this. This thing can be expressed in terms of this measure, and this thing expressed in terms of this measure. So I don't know if I should write down an explicit formula, or maybe it's fine. So okay, it's not a very difficult task. And so we found two necessary conditions for a group to be L1 noise sensitive. And okay, it has to be Liouville, and it has to have no morphism to R. So a very natural candidate at this stage. And maybe I will state it clearly. Very natural candidate is the Grigorchuk group. Right. So okay. So here is a conjecture. The Grigorchuk group is L1 noise sensitive. And okay, why did I want to be vague in the beginning? Okay, I've been precise. Sorry?
But if you have a linear Schreier graph, the Grigorchuk group is not a problem.
No. No. This will be clear later. So
Could you remind, so noise sensitive is when the limit is zero?
yes. And okay. Okay, I didn't want to state it very precisely. I would have preferred to state this conjecture a bit more naively first. Then, so what is fascinating about noise-sensitive system? A noise-sensitive system means you have a system, and you perturb a very little bit the input, and the output is completely random. So this is really absolutely non-stable system, and somewhat they're interesting because there are somewhat systems that are not coming out in physical law, like you would not detect it. And my first evidence that the Grigorchu group is noise sensitive, okay, maybe ridiculous as it sounds, is that the Grigorchu group does not appear in nature. In my opinion, the Grigorchu group is something only mathematicians know. It's
You're lucky he's not here.
I mean, you can take it as a compliment too, right? Because it means you really have to have great ideas to come out with this.
You can, but he wouldn't.
That's true. I agree. So this is the first maybe naive remark, and okay, I state it as a conjecture, so it means I'm not able to prove it. So you see, you have small groups and big groups, and you try and you fail, and what do you do when you have a math question you can't solve? Well, you change the question. So let me change a little bit the question by defining another notion of noise sensitivity related to entropy. So here is a definition.
There's no example where you can do that.
Okay, so I started a list of examples here. I'm not finished with that list, but okay. so maybe now I said enough that you can try to guess examples here. Maybe you'll be disappointed, but there are. So okay, let me define entropy noise sensitivity. So we say a group is entropy noise sensitive if, well, we compute the entropy of the noised sample, and we compute it knowing the precise sample. So if I tell you what is the exact output, then you can compute the entropy of the noised sample, and we want to compare it with the entropy of just one sample. And we say it's entropy noise sensitive if this tends to 1 as n tends to infinity, and this has to be true for any O between 0 and 1. So maybe I should remind what is the definition of conditional entropy. So just, I guess most people know it, but as it can be expressed fairly easily. So that's, well, the definition, I guess, is this: the expectation over x of the entropy of y, knowing that x takes some precise value g. And maybe, okay, if you don't know this, at least you know the definition of classical entropy. So it's the entropy of the couple xy minus the entropy of x. So we can have this definition. And okay, so maybe you agree already that this is less demanding than the first definition, because having information on the entropy of a measure is much weaker than having information on its L1 distribution. But I still want to make this even weaker.
Well, they coincide in the case of plane random walk.
Sorry?
They coincide, these conditions, in the case of plane random walk.
Plane?
Well, there is the entropy criterion, which says that these ratios just zero and we will go to zero.
So be careful of the normalization is by the entropy of the random walk.
Yes.
So, okay, probably the next comments will make clearer your point. So, So let me even say partial entropy noise sensitivity. NS. This is if there exists some positive constant such that no matter how little you noise, then the entropy of the noised sample is at least a constant times the entropy of xn. So, okay, this is very little, but still, I believe this is already significant. So this says even if so there's a constant c, let's just to figure out, say 1/3, such that if I noise maybe 1 out of 1,000 thing, already there is 30% of the information you cannot recover from the sample xn. So that's already significant. And okay, maybe as a little game, let me try an experiment on you. So I chosen a piece of text of 28 symbols. So 28 symbols among the letters, and the space is also a symbol, and punctuation marks are a symbol. And I noised it 25%. So I'm going to write the resulting perturb thing. So obviously it's a question mark, and
but this is like giving us the steps of the walk with the noise and not the final result of the walk.
sorry.
You're giving us each step of the walk with some noise as opposed to just the product.
Yeah. So the result of the walk is the meaning of the sentence. Right. Okay, this can be commented on for very long, and of course we are not the experts on this. So, okay, so maybe now come back to this list of examples where things are entropy noise sensitive. So let me just check how much time. Okay, half an hour. That's fine. So, well, of course, finite groups are still entropy noise sensitive. And now, okay, like examples. Now Z is entropy noise sensitive. And, well, the reason is you can compute explicitly, right? The entropy of a random walk on Z, this is really a constant times log n plus little o, and the yn rho, then there will be an independent part of length rho n, so you will have log of rho times n, and this is the same. So this is just very easy. Maybe, okay, now we can try something in the middle between free groups and say abelian groups. So let us try what was qualified yesterday, the least exotic example. So for instance, the Lamplighter group. Right. So if you look at the Lamplighter group, right, well, the theorem is that this Lamplighter group is entropy noise sensitive. And let me try to explain this. So, so what happens? So you have the random walk on the Lamplighter xn, and so that's a product. And these things are, let me say, okay, I take the switch walk switch random walk. So at each time you switch a lamp on or off and you move randomly. So xn is this, and now we are going to noise it. So there are two types of noise, right? There is the noise coming from the change on the walk and the change in the switch. And okay, I hope you agree that it's enough for me. So I first, the n is when we refresh the walks, and then we refresh the lamps to get to this yn. So there's an intermediate space, and you know, if I'm going from here to here, I hope you agree that the entropy of the if I want to know the entropy of yn knowing xn, then it's bigger than the entropy of yn knowing zn. So I will focus only on this one. You can actually prove this, but let me not do this. So now I want to compute the entropy of yn knowing zn. Now what happens? So what happens is I have a trajectory of the random walk on z, and then you have to switch on or off some lamps. And if you look at a particular place x, then what do you see? Well, what you see here is a product of increments. So that's the product of terms in z mod 2c, product of how many terms are there, factors, sorry, not terms, factors, in z mod 2z that are independents. Well, that's the local time of the random walk. So you have the local time of the random walk here. Now, if you take one position like this, what is the probability that the lamp here was refreshed? So this probability, so the probability that the lamp at x is refreshed, this is precisely 1 minus 1 minus rho to the local time at xn. And now we have the Reinheit theorem that tells us that in most locations visited by the random walk, then this local time is going to infinity. So let me not detail here, but the Reinheit theorem, this implies that the entropy of yn knowing zn is bigger than the expected side of the range of the n, and it's well known that this is comparable, that this is really like equivalent to the entropy of xn. So that's enough to look at the lamps to have this. And okay, here is a second argument why the Grigorchuk group should be noise sensitive, is that in a sense the Grigorchuk group is a pure lamp thing. Maybe okay, Gidi is laughing, but in a sense, in first approximation, this should be the case. And now, if we look at what is the information you can recover from this, well, of course, the final position, right? It's given by this morphism to z, so we can recover it with some precision, and the leftmost and rightmost values of the range we can recover approximately also. Right? But this is basically the all information that you can get. So
Seems a lot related to the Ringel property. The same argument would work in 2-dimension, but it wouldn't work in 3-dimensional model.
yes, I agree with you. Okay, so I'm trying to keep this entertaining. I know that. So okay, let me go on this example using lamps, right? And maybe not give too much details about it, depending on how much time there is. Okay, so you can easily adapt it to get the following theorem. So now you take the Grigorchu group, and okay, you modify it by taking the risk product over the Schreier graph of this vertex 1 infinity. So Omer Angel defined the Grigorchu group this morning with this tree structure, and he had this picture that to define the Grigorchu group you have this ray, and then at infinity you have some point here, and you can look at the permutational rest product of the Grigorchu group over this. This was first considered by Bartholdi and Herschler to get a precise computation of growth functions, and this was used further on by, for instance, Gidi and Balint Virag, and also myself. And this is really. Sorry. No, I think not. It's like customary to take this one, but probably it does not matter. And well, this is partially entropy noise sensitive. So let me be brief on the argument. It's essentially the same argument as here. So sketch of proof. So by Gidi Amir and Balint Virag, we know that the entropy of the random walk here is comparable up to explicit constants to the expectation of the size of the inverted orbit. Let me not define the inverted orbit and say no more that this is the analog of the range.
So is it important which random walk to choose here?
Yes, you're right. This is again. So here it's not so important for the Lamplighter group, I guess. Any symmetric would do it. Here it's important that we take the switch walk switch again. You're right. This is an important point. I will explain. So you have this, and what happens? So we could do the same here if we had some information about the local time. We don't have information about the local time, or I mean, possibly we could get some, but it would require some work. But there's always an obvious bound here, is that this is bigger than rho, right? So it's obvious, it's an easy bound, that in this situation, this is bigger than rho times the expected size of the inverted orbit. But then this is not satisfying because we want here a constant that does not depend on rho. And the point is, if you take this switch walk switch random walk, a specific one, then it's known that this random walk is self-similar in the sense that when you look at a section, you see the same random walk, but it is slowed down by a factor of time. And in the same process that it slows down time, the effect is to increase this rho. So if you look at sections, so in section 1, the factor is not rho, it's rho prime, and you can completely explicitly compute it. Rho prime, this is 1 minus rho over 1 plus rho. This is strictly more than rho. And okay, this is like standard dynamics, and you give yourself a number between 0 and 1, say 1/2, and then if you iterate this enough, you get bigger than 1/2. So we get 1/2 here. And okay, what remains is to check that the general inverted orbit, you can obtain its size just by picking up the several.
But the importance of taking this walk is for the proof, or do you think
I think it's only for the proof. But
partial is really partial, or also just for
so okay, as I said, I conjecture that the Grigorchu group is actually noise sensitive. So it should. But in practice, for instance, you cannot adapt this to the Grigorchu group. And for instance, we don't know what is the entropy of the Grigorchu group. Right? We know it's at most root n, but there is not even a significant lower bound to my knowledge. So okay, let me. So this is really like you know, if you know this paper, it's very easy to come out with this, but then getting more would be substantial. And okay, I want to state another theorem, also not very difficult. So theorem. If G is partially entropy noise sensitive, then it is Liouville. And okay, maybe I don't know how much time there is, so maybe I should skip the proof of this. But it's not really difficult. So the idea is to use this entropy criterion due to Vadim Kaymanovich and Anatoly Vershik. So if it's non-Liouville, then you have some positive entropy. And then somewhat if you take large enough subwords, then they tell you all the information of the entropy. So I'll skip the proof of this one. And I want to go down to the, okay, so basically that's almost all the information, all the statements that I can give. But there is still one more. But first I would like to state the conjectures. So there are two conjectures. Let me start. Maybe I think the second one is a bit less interesting, so I state it first. So Liouville. So we know that partially entropy NS, this implies Liouville. And of course, entropy NS implies partially entropy NS. And the question is whether Liouville implies entropy noise sensitive. And I would bet that these are equivalent. And at least if it's not, it would be interesting to find counterexamples. But here is the wrong argument for this. If it is Liouville, then again by this entropy criterion, the entropy criterion tells you that the amount of information in 1 digit is 0. So the amount of information in 2 digits should be 0 and 3 digits. So you expect that you really need to read the whole thing. But this is not correct because you're not doing things at the right scales, right? You are counting this at the linear scale, whereas we want it at the actual entropy scale. So it would, if this is true, this would require serious upgrading. But still, okay, let me state it as a conjecture. And the second conjecture is the following. Assume we have a group Liouville and no morphism to R. Then this implies L1 noise sensitive, and a priori I would say this for any new finite support. No more morphism to R. So you might want to state it like this. And then, okay, this is not correct. Because you need to, sorry? Okay, let's say Z. Let's say. Not really. It's, okay. So it's virtual. So if I don't put the word virtual here, then this is no longer true. So, okay, I will prove this. So I will find a group. So it means there is a finite index subgroup that has a non-trivial morphism to Z. So if I remove this virtual, so I have to give you an example. Promised you 2 examples. So this is the second one. I must give you an example of a Liouville group which has no morphism to Z, and it is not L1 noise sensitive. So this is really not the surprising thing. So okay, here is the theorem. So okay, an example of a group with no morphism to Z is the infinite dihedral group. And you take the simple random walk is not L1 noise sensitive. So let me explain this proof. So what does the Cayley graph of the dihedral group look like? So you have, say, I draw two colors. Say white is for A and red is for B. It looks like this. Now, if I make a simple random walk, so I'm here at some position, right? And then the next move is either take the B path or take the A path. Right? So imagine I'm told to do the B path. I'm supposed to move here. And it is noised, and I do the converse. Then the change is plus or minus 2. Noise is plus or minus 2. So it's like in the abelian case, right? Like in Z. So it's not L1 noise sensitive. And now can you guess the little b here? Now if we take a lazy random walk, lazy simple random walk, then this actually becomes L1NS. So it's just as simple as that. You take a lazy simple random walk on the dihedral group, and then it's noise sensitive. So in particular, the corollary is that this depends on mu, right? It strongly depends on mu. And let me try to explain why this is noise sensitive. Now, this is like the simple random walk. And in the lazy case, imagine you are here, right, in the same position, and I want to tell you to do B, A, B, A. So if you listen correctly, the three of them, then you'll end up here. But imagine there's a mistake and you hear 1 here. Then you don't move, but then you should follow A. So not the red one, but the blue one. Oh, this is white. So you move this, and then what you do is this. So the effect is if you make a mistake in the lazy simple random walk, the effect is to put a mirror on the trajectory. And now maybe, okay, it's technical to get to L1NS, but I mean, morally you can guess that if I take a trajectory of the simple random walk and I put mirrors very regularly, then the output will be completely decorrelated of the first input. So this is this is roughly the idea of the proof. And before I stop, let me comment on one thing, is that we considered this example and worked it out, but really the important thing here is that this is a finite extension of a abelian group, and the finite thing, it has an action, and the noise sensitivity of this finite thing is enough to make the whole process noise sensitive here. So I believe a very concrete task is how much can this generalize if you take virtually abelian groups. Then, okay, this is a natural task to understand this phenomenon. So I mean, you have a probability. Okay, we really worked it out in the case where you have a probability 1/3 to take B, 1/3 to take A, 1/3 to take neutral trivial element. No. I think this is just, you can make these things work easily, but okay, to what extent, then we need to work this out. So I'll stop here.
Question? Yeah, so you assume from the very beginning that your measure is generating, so that the subgroup is supported the whole group. Where are you using this condition?
Nowhere. I mean, maybe it's just for safety of mind. But of course, I mean, if you want to say something about the group, right, it has to be generating. So no? Okay.
No, because that's a restricted condition. So it means that you only restrict yourself to a certain class of samples.
So okay, so you think this assumption is like not necessary? I mean, I don't think we used it. No, but okay. Yes.
Do you think that in any of your definitions, is there any example of the group where the
The value of?
The value of rho to attach to that array.
So far the way we studied things is what happens when a row becomes very small, and we want things to hold when a row becomes very small. So okay, you can play with this parameter too, and this raises lots of questions, but okay, they are to be figured out. So I should say maybe that okay, this could almost have been a second open session problem, right? When you think about it.
The conjecture that we on the reducibility is that it's L1 non-sensitive regardless of the generators.
Yes.
We don't have another example where it's true regardless.
Okay. So far we have one example, right? It's, okay. For
For L1, that's the only.
that's the only for L1 that's the only example, right? So I mean possibly there are some like virtual, because here you see this dependence is on this simple random walk, and this like +2 -2. This is like some error correcting code, right? Anyway, if you make a mistake, you're still in the good direction somehow in your environment. So, but this might not be, you know, if you take virtually a billion groups, what happens? We don't know already.
You think that this sensitivity with respect to the generating set doesn't always, I mean, we have this conjecture that it's L1 noise sensitivity is basically the same as U-Bill, except, and the right side is, if the right side depends,
You will and no.
well, so there is the morphism to that. So really that's the thing that makes the mu important.
Sorry. What makes the mu important?
Yes, but so the dependence on the generating set,
Yes.
L1 noise sensitivity, is there only if you have a morphism onto that, not otherwise. That's
Yeah, that's okay. This is consequence of the conjecture. So okay.
Should there be a difference between the partially entropy non-sensitivity and regular? The partially is important here, or is it?
So the conjecture is it's not important, because somehow it would be. I mean, it would be very interesting if it were important, but
This is the same as,
yeah, yeah, because.
So you don't have an easy thinking that
So-
ENS would not be ENS.
No. I mean, I would be surprised if you could get like 30%, but not all of the information. But so one observation on this is that, so okay, do you have this Liouville condition, and then what is somewhat striking to me is that having a morphism to Z is really a resistant to noise sensitivity, right? This is really very strong, and if there are some groups that are not L1NS, then is there as a nice reason as a morphism to Z? I don't know.